Hello everyone, myself Dr. Priyabrata Manna, Department of Chemistry, Brenner University. Today's our topic is infrared spectroscopy, that is also called IR spectroscopy. Now, now in the introduction part, what is spectroscopy? Spectroscopy, in a one sentence, we can say it is the interaction of electromagnetic radiation with the matter. What is electromagnetic radiation? Electromagnetic radiation is a radiation where two types of radiation, electric field and magnetic field, two field, electric field and magnetic field, they are propagated in the form of wave, right? So they are in perpendicularly propagate. Now those electromagnetic radiation, when it interact with a matter, some of this electromagnetic radiation is absorbed by this matter and rest of the part is transmitted, and that transmitted part is recorded by the detector, and on the basis of how much percentage is transmitted, or maybe on the basis of how much amount is absorbed, on the basis we can characterize the any sample, mainly organic sample. And spectroscopy is a part of science where it is utilized to find out the structure of any particular or unknown sample. Now question is that during any experiment, whatever the reagent we use, that reagent give us some product, but we don't know, we can expect what kinds of product is formed, but that might not be, because the product we can't characterize, we can't specify that product, and we can't without analysis that what kinds of product it is, that what kinds of product it is only is characterized by the so many process, but one of the process is spectroscopy. Today's here we will famous scientist Maxwell first invented this electromagnetic radiation. Electromagnetic radiation, where two fields are there, electric field and magnetic field, they are perpendicular propagating a particular wave-like nature. And when this electromagnetic radiation interact any matter, then we get different types of spectroscopy depending on the energy of the electromagnetic radiation. And depending on the electromagnetic radiation energy, there is lowest frequency region is the radio wave, and when it is interact with the matter, it will radio frequency, it will generate radio frequency. Then greater than radio frequency is microwave, that is rotational spectroscopy. When rotation microwave electromagnetic radiation react with the interact with the matter, so it will generate the microwave. One of the application of the microwave, the we use the microwave and we use in our daily life. IR spectroscopy, that is nothing but vibrational spectroscopy, and when this IR electromagnetic radiation is interacting with the matter, that generate IR spectroscopy. Now question is that today's our topic is IR spectroscopy. Higher energy spectroscopy also, they are visible. UV spectroscopies are there. You all know UV spectroscopy nowadays used in a filter instrument, water filter instrument. And X-ray is very one of the medical purpose we use the X-ray spectroscopy. Gamma ray, cosmic ray, they are heavy high energy spectroscopy. Those are harmful for the body. And you all know from radioactive element, we are normally get this gamma ray or cosmic ray, which is very harmful. It is one of the reason for the cancer in our body. Now we will concentrate on the vibrational spectroscopy. Vibrational spectroscopy or IR spectroscopy, that is called infrared spectroscopy. It is the electromagnetic radiation is in the range of mainly 1.7 electron volt to 1.24 mega electron volt, that is photon energy, and the range of wave number 400 centimeter inverse to 4000 centimeter inverse. Within that range, so many frequencies, IR frequencies are there, and these IR frequencies are responsible for whole spectrum. When we are saying it is a spectrum, that means there is so many spectra are there, and those spectra correspond to different different frequency of the IR spectroscopy. So within the 400 to 4000 centimeters, so many different energy of frequencies, wave numbers are there. If it is, we say in the range of wavelength, it is 750 nanometer to 1 millimeter in the range. So IR spectroscopy particular, when this 400 centimeter inverse to 4000 centimeter inverse wave number electromagnetic radiation incident on a matter, some part of this particular incident radiation is absorbed by that sample and rest of part is transmitted. And this transmitted part is goes to the detector of the spectrometer, and from where we able to understand the what kinds of material is present over there, and most of the time not every molecule is responsible for IR activity. Some of the molecule are IR active, some of are not. Most of the homonuclear diatomic molecule, those are when IR's energy is incident on it, there is no change in the momentum, dipole moment changes are there. So they are never show the IR activity. Those particular compounds show the change in dipole moment. They are IR active molecule. So this is, and now question is that if you take any compound, that compound, say covalent compound, there is so many bonds are there. So those bond with respect to the molecular axis, that here you can see one example is given over there. So for here is a compound is CO2 is given. Here carbon is black color and oxygen are red in color. So when this is the molecular axis, this is your molecular axis. So when depending on the vibration of this oxygen molecule with respect to carbon, so there is normally different types of vibration within, and these different types of vibration associated with the different energy, and that means associated with the different types of frequency. So So depending on that, there is mainly along the axis there is two types of vibrations are there. One is symmetric stretching, another is anti-symmetric stretching. I am giving one example. See, if this is my hand, right? This is my hand. This is bonded. Okay. So when this is the bonded atom, these two, this is carbon and this is two oxygen, right? Now, when it is symmetric stretching means this, go out, go in, go out, go in. So this is symmetric stretching. And anti-symmetric stretching, one is go out, energy is come in. Then it is go out, it is come in. This is anti-symmetric stretching. Now both these things are different energy associated. Okay, this is one thing. Now another thing is that it is whatever the stretching it is in the plane of the molecule. Now if it is along the in the axis of the molecule, if it is along the plane there is two types of, one is rocking, another is twisting. And rocking is like that, that is rocking, and twisting is there, these types of twisting. So so many processes are there that associate with different types of energy, that if there is different bond, different atom is attached with that, so they are having, that is associated with the different energy. And when infrared electromagnetic radiation is incident on that particular molecule, it will show different types of characteristic and different types of absorption and different types of transmittance in the spectrometer. So here is twisting, bending types of vibration. Bending is a in plane bending is there, seesawing and rocking, and out of plane is nothing, twisting is giving. So there is different, that is these types of one, and another is this types of. So there is different. Another is seesawing, that is like this. Seesawing is like this, and then rocking is like this. So different types of vibration. That vibration is coming from bonding within the molecule. So these types of vibration is associated with different energy. Now, when you incident 400 centimeter to 4000 centimeter electromagnetic radiation on that sample, some of that particular is absorbed by the sample depending on the what kinds of vibration present over there. Here I am mentioning here one IR spectrum of my PhD work. So transmittance is with respect to wave number is given. So if you look at very carefully, it is 100%. Up to this is 100% transmittance. That 100% transmittance means that whenever you infrared electromagnetic radiation, you giving this sample, everything is transmitted, nothing is absorbed. Now look at that, in that position some of portion is absorbed and rest of the part is transmitted. So that particular characteristic will give you what kinds of bond present within that. On the basis of I am giving, there is so many results here. So OH stretching transmittance frequencies wave number is given over there, 3200 to 3635 in. But likewise, saturated CH is given, unsaturated CH stretching frequencies are given. So what is the main aim of this process is that we want to find out which kinds of vibrating bonds are there, which kinds of atoms they are bonded within the compound. So in any types of reaction, whatever the product is formed, we are unable to understand what kinds of product is naked eye, but with the spectroscopy analysis, now we can say what kinds of bonding present over there. So that is the main utility of the IR spectroscopy. Now, the question is that which particular type of sample compound will show, not all the sample will show IR spectroscopy. Those sample will show IR spectroscopy when electromagnetic radiation of IR range is incident on that sample. It will generate a change in dipole moment. Most of the diatomic molecule, homonuclear diatomic molecule, like I am giving example oxygen, nitrogen, fluorine, like that. So they never show IR activity because there are no change in dipole moment. So they are IR inactive. And there is some, most of the heterogeneous diatomic molecule, they are always changing dipole moments, HBr, HCl, Hi, they show the IR activity. There is some heteronuclear diatomic molecules are there, carbon dioxide, CH2, HF2. If it is symmetric stretching, they never show IR activity. But if it is anti-symmetric stretching, we have already discussed this thing for CO2. So they will show to some extent IR activity. And most of the heteronuclear diatomic nonlinear molecule, they show IR activity like H2O, H2S, and most of the polyatomic molecules, NH3, CH4, they are mainly unsymmetric stretching show the IR activity. So with the help of this IR activity, we can actually characterize the organic sample. This is our main purpose of IR spectroscopy. On the basis of it, we can able to find out the how many vibrating modes are present. That is designated to the degree of vibration of the molecule. If the molecule are linear molecule, then if n is the number of the atom present within the compound, so any atom, n is the number of atom of a molecule of that particular compound, then For linear molecule, the total vibrating modes will be 3n minus 5, and for non-linear it is 3n minus 6. Here for a water molecule, by applying this equation, it is it is a non-linear, so that is 3 into 3 minus 6, 3 vibrating degrees of freedom or vibrating modes are present over there. There is some problem is given over there, can go through it, so it will help you to find out. Now IR stretching frequency, how can we calculate? Normally we will calculate this IR stretching frequency by the help of Schrodinger equation. This is complex equation, so only we give here the stretching frequency nu is equal to 1 by 2 pi k by nu. That is nothing but here nu is nothing but reducing mass, that is 2 atom, their mass if 2 atom having mass mb. So reduced mass will be Ma plus Ma into Mb divided by Ma plus Mb. So, and K is the force constant, and we can calculate the vibrational energy also with respect to joule and wave number also. So that is nu plus half of H nu oscillation. That in that manner we can also find out the stretching frequency of the IR spectroscopy. Now from the Schrodinger equation we can the allowed transition for IR spectroscopy. That means whenever a molecule is given to the IR spectrometer electromagnetic radiation. So how much it is absorbed that particular energy and go to the higher energy state, and that is will be delta nu. That level will be plus minus 1. And now at the last, the application of IR spectroscopy. Normally, I have already told that it is mainly used for the find out of what kinds of bond present within the molecule. That is determination of the structural information of the compound, various compound, and it is also detect the intramolecular hydrogen bonding, and it's also applicable for the kinetic study of the kinetic study of a chemical reaction. And it is also used for the fingerprint. It is one of the utility of the find out the different function present. I have already told. So this is all the application. Here some problems are given to which is having the higher IR stretching frequency. According to the formula, IR stretching frequency of any molecule is directly proportional to the force constant of the molecule and directly proportional to the bond strength of the molecule. That is why if triple bond is present, that IR frequency, stretching frequency will be much more higher rather than double bond than the single bond. So that is why it has the highest stretching frequency will shown by the ethene with respect to the ethane, where in ethene that is double bond is present. So that is the higher force constant is there, that is it will show the higher stretching frequency. And here is another problem, select the compound with the higher stretching frequency, explain the reason. Propanol and propanol. In between propanol and propanol, propanol has the higher stretching frequency because in propanol the functional group is aldehyde and in propane it is the functional group ketone. In ketone, the presence of plus I effect due to the presence of two alkyl group lowers the C double bond O bond strength, while in the aldehyde there is plus I effect due to the presence of the hydrogen and one alkyl group. Thus in aldehyde, propanol has higher IR stretching frequency than the ketone in propanol. And another question, in 2-butanol and but 3 but in but 3 C double bond C bond is there conjugated with the C double bond O group. Hence, C double bond assumed to single bond character. As I already discussed, as it is so single bond character, that is the frequency will be much more lower with respect to the but 3 So that is the main things of all this problem related to IR spectroscopy. So one thing I concluded here, IR spectroscopy, one of the spectroscopic technique by which we can able to find out the structure of the molecule, and it is one of the electromagnetic radiation that interact with the material, and some of this IR electromagnetic radiation is absorbed by that by that compound, that is the absorption will be the characteristics of the compound, and rest of the transmitted, and we get the transmitted versus the wave number graph. From that graph we able to find out which kinds of functional group or which kinds of bond is responsible for that transmittance with the respect to the transmittance percentage, and in that way we will characterize the sample. So end of this session. Thank you so much. Thank you.